Hello, welcome to this series of short videos on the action potential. In this first video, we will look at the definition of an action potential and we'll begin describing the action potential. In the subsequent videos, we will look at the ionic basis of the action potentials. Now, we have looked at the origin of the resting membrane potential earlier, and we saw that the resting membrane potential comes about due to three reasons. One being the differences in the concentration of ions across the cell membrane. For instance, the far greater concentration of potassium inside the cell compared to the outside, and the far greater concentration of sodium inside versus outside. The second factor, of course, is the differential permeability of the membrane for the ions. In the resting state, the cell membrane is much more permeable to potassium than to sodium, and therefore as potassium moves out of the cells, it carries positive charges along with it, leaving behind negative charges inside, resulting in a polarization of the membrane. And because there is a far greater amount of potassium movement compared to sodium movement, ultimately the membrane potential is close to the equilibrium potential of potassium rather than that of sodium. So these two things put together actually suggests that the membrane potential is a weighted average of the equilibrium potentials of the ions involved. Weightage, when we say weightage, what we mean is that the equilibrium potentials influence the membrane potential to the extent that to the extent of the permeability of the membrane to those specific ions. So because the membrane is more permeable to potassium in the resting state membrane potential is influenced by potassium to a much greater extent than that of sodium. The third factor, of course, is the activity of the sodium-potassium pump, which restores and maintains the ionic concentrations, and it does contribute a small but important element of the resting membrane potential. Now, we'll continue the same experimental situation that we used to understand resting membrane potential. So we have a voltmeter with recording electrode shown here in blue, which has been inserted into the cell, and we have a reference electrode which is shown here in purple. The cell itself is in the resting state, and as you can see, there are negative charges on the inside and positive charges on the outside. Therefore it is charged, so there is a certain amount of resting membrane potential. Now what we add to this experimental setup is a stimulating electrode. A stimulating electrode connected to a current source, and this current source is able to inject currents into the cell. So one could inject a positive current, that is positive charges into the cell, or one could inject a negative current, that is say negative charges into the cell. So this completes the experimental setup required to understand the origin of membrane potential changes, and particularly the action potential. Now we'll begin by recording in a cell like, say, a skin cell or a liver cell. Now these are typically what are called as non-excitable cells. The majority of cells in the body are probably non-excitable, and we'll see what happens when you inject currents of different types into this kind of cells. So this is the chart, and as usual this is the x-axis with time in milliseconds, and this is the y-axis with voltage, membrane voltage in millivolts. This is the zero line, isoelectric line. Now this is the line representing the resting membrane potential, and then we'll arbitrarily say that this particular cell has a resting membrane potential of about -70 millivolts. Over here we'll see the type of the stimulus being applied. This will be a record of the current being injected into the cell. So the stimulus could be a positive stimulus, which is stepping up, or a negative stimulus, injection of negative charges, which would be a stepping down. Alright, let's begin now. Now you can see that there is a certain number of negative charges inside, and similar number of positive charges lined up outside, leading to a particular resting membrane potential. What happens if you stimulate a positive current into the cell? Now when you stimulate positive current into the cell, it is adding positive charges, and these will distribute on the inner side of the membrane, and when you are adding positive charges, they neutralize the negative charges, and therefore there will be a reduction in the number of negative charges inside in effect, and it would lead to a reduction in the number of positive charges aligned outside too, isn't it? and therefore overall there will be a reduction in the polarization. Let us see what happens when you inject that kind of current. So that is a positive current being injected. Current injection is starting here, continues for some time and ends here. So when you do that, what you see in the membrane potential will be recorded over here, and we can see that the injection of the current reduces the number of negative charges inside, and what you get is a change in the membrane potential. The membrane potential goes from around minus 70 millivolts to something like minus 65 millivolts. It stays there as long as the current is being injected, and when the current injection stops, it drops back to the resting state. So going from minus 75 to say minus 70 or minus 65, so this is going from a greater negativity, minus 75, to a lesser negativity, say minus 70 or minus 65. So this is a reduction in negativity. It is a reduction in the polarization of the membrane, and therefore we call this kind of responses as depolarization responses. The membrane potential becoming less negative, depolarization. And a stimulus which results in such depolarization, which is essentially addition of positive charges into the cell, is referred to as a depolarizing stimulus. Now, what would happen if you inject a negative current into the cell instead of a positive current? When you inject negative current into the cell, a step down stimulus, there is greater negativity added to the interior of the cell. These larger number of negative charges line up against the membrane, and there would be an alignment of positive charges on the outside, so the overall polarization is greater, right? Let's see what happens to the membrane potential. So there is greater negative charges lined up inside the cell now, and the membrane potential actually drops from minus 75 to say minus 80. So the membrane potential goes from negative value minus 75 to even more negative value minus 80, and it remains at that heightened negativity for the duration for which the stimulus current is being injected, and then drops back to the resting state. So this kind of a response is referred to as a hyperpolarization response. So where you have the membrane potential becoming more negative, hyperpolarization, as opposed to the depolarization we saw earlier. And a stimulus which results in hyperpolarization is referred to as a hyperpolarizing stimulus. What happens if you inject a stronger current? In this case, let us inject a stronger negative current. The response is greater. You have hyperpolarization from minus 75 this time to something like minus 85. So there is a greater or a stronger response. And if the stimulus is even stronger, say double the stimulus strength that we used the first time around, then the response, the membrane response is double the response that we saw for the first stimulus. So what this shows is that the membrane potential responses are in step with the stimulus strength. They are proportional to the stimulus strength, and it will be the same for this kind of cells with depolarizing stimuli too. As you increase the strength of the depolarizing stimulus, the response is also increasing in a more or less proportionate manner. So you double, for example, if you double the strength of the depolarizing stimulus, you get double the membrane response in terms of voltage changes. So if you notice here, there is a relationship, a linear relationship between the stimulus strength and the response magnitude. Increases in stimulus strength gives you proportional increases in the response magnitude. These kind of responses, where the membrane potential responses are changing in proportion to the strength of the stimulus, are referred to as electrotonic potentials. Electrotonic potentials are also called as graded potentials or local potentials. Why are they called graded potentials? Because the responses are graded in relationship with the stimulus strength. Why are they called local potentials? Now we'll discuss this aspect a little later again. They are called local responses or local potentials because these changes occur at the point of stimulation in the cell membrane, and they get conducted to a short distance. All electrical signals get conducted and these also get conducted to a short distance from the point of stimulus, but they tend to die out quickly. They tend to reduce in the magnitude as you move away from the point of stimulation. So that these responses are localized. You don't get to see them from a great distance from the point of stimulation, right? So this kind of electrotonic potentials are seen in almost all types of cells with a resting membrane potential. You would get depolarizing and hyperpolarizing responses which are graded. So non-excitable cells like liver cells, skin cells, they have only this kind of graded electrotonic potentials. However, other cells like neuronal cells or muscle cells, these are excitable cells, and these excitable cells have additional properties. Their membranes have additional properties which gives rise to other types of responses. Let us take a quick look at that. So now let us say that this is an excitable cell, and we are repeating the same kind of injection of hyperpolarizing stimuli and depolarizing stimuli in an excitable cell like a neuron. In excitable cells, when you look at the hyperpolarizing responses in response to negative currents, again you see that there are increases in hyperpolarization responses which are in proportion to the increase in the strength of the hyperpolarizing stimulus. So the hyperpolarization electrotonic responses are similar to that seen in non-excitable cells. There is a linear relationship between the strength of the stimulus and the magnitude of the response. However, when it comes to depolarizing responses, there are differences. Let us begin with a small depolarizing stimulus, and you have a small depolarizing response. If you increase the strength of the depolarizing stimulus, you notice here that there is an increase in the response magnitude, and the increase in the response magnitude is actually a little more than what was expected in a non-excitable cell. So remember, these are excitable cells. And if you have an even further increase in the stimulus strength, notice that this stimulus is roughly double the first stimulus. The response, however, is a little more than double, isn't it? It's a little more than double. Now, this means that for depolarizing stimuli with increasing strengths of depolarizing stimuli, the depolarizing responses are actually growing out of proportion. There is an enhanced response with every step up. Now that is the key to excitable cells. It's not only in the magnitude. If you look carefully, even the time it takes for the response to begin and to die off is also a little different, isn't it, compared to the excitable cells. Now if you have a stimulus strength which is even stronger, and then you see something which is completely different. Now this is something which really sets apart excitable cells. So if the stimulus is beyond a certain level, then the membrane potential begins to increase like earlier, slowly, but then all of a sudden the membrane potential just shoots away upwards, and it goes towards zero, crosses the zero line, and reaches something like plus 20, plus 30 or plus 40 millivolts, and then rapidly dips back towards the resting state. And as it dips back towards the resting state, it slows down a little, takes its time, and in fact it may actually dip below the resting state and then stabilizes at the resting state. Now this completely different response is referred to as action potential. Now as opposed to electrotonic potentials, local responses, these are action potentials. A disproportionate response, a very rapid depolarization response, which is followed by repolarization. So this is what an action potential is, and this is the fundamental difference between electrotonic local response and action potential. We'll understand the basis for this in the next video.